Welcome to the Crazy Hat Chemist. So here we are with another awesome video here. And I hope you're having a good morning, a good afternoon, and a good evening, because this is the place to be if you want to learn your chemistry. Anyways, I am the Crazy Hat Chemist, and today's video is sponsored by none other than the Crazy Hat Chemist. That's me. Anyways, so here we go. We're going to keep on going here, and we're going to do an awesome video today on periodic trends. So before we get started on periodic trends, I'm going to assume one thing, and that is you have a periodic table. If you don't have a periodic table, then how can you do periodic trends? That's just impossible. So here we go. We have our periodic table right here, and we are going to do some periodic trends. So without further ado, we're going to get moving on this video here, and we're going to slide this over here and figure out what our first question is. So question number one is, how is the modern periodic table organized? So again, we're going to flip over to the periodic table, and we're going to see if we can answer this question right here. So here is our modern periodic table. And so the primary level of organization of the periodic table is according to atomic number, and that is the number of protons. And so this goes back to another unit, and this is AXZ right here. And X is the symbol of the element. A is the atomic mass, which is actually the sum of the protons and the neutrons. That is the atomic mass. And Z is going to be the atomic number. And what is the atomic number? That is the number of protons. So let me give you an example here using this symbolic notation. We have hydrogen, and that would have an atomic number of 1 and a mass of 1. That is one of the many of 3 total isotopes of hydrogen. And here is another isotope of hydrogen. This is deuterium. And then this is furthermore another isotope of hydrogen here. This is tritium. Now I want you to notice that all 3 of these isotopes of hydrogen have the same atomic number right here, and that actually identifies the element, what it is. Okay, here's another symbolic notation, and that would be one that you should be familiar with here. And this is called carbon-12. And how many protons and what is the atomic number? How many protons is 6. What's the atomic number? 6. In fact, the periodic table is organized according to atomic number. So that is, for example, 1 for hydrogen, 2 for helium, 3 for lithium, 4 for beryllium, 5 for boron, 6 for carbon, 7 for nitrogen, 8 for oxygen, 9 for fluorine, 10 for neon, 11 for sodium, 12 for magnesium, 13 for aluminum, etc. Right? So the atomic number is equal to the number of protons. Okay, this level of organization was done by Henry Moseley. So I'll write down his name since that's, of course, very important in this discussion. So Henry Moseley. And he did this in 1913. Now, the periodic this is how our modern periodic table is organized. And there was another scientist that actually designed and organized the periodic table, and he's the father of the periodic table, Dmitri Mendeleev. And in 1869, he organized the periodic table and he published it in a textbook. And Dmitri Mendeleev is the father of the periodic table, and he actually organized the periodic table according to atomic mass. Our current periodic table, as you can see here, highlighted in the yellow, is according to atomic number. The next level of organization on the periodic table is done by what are called quantum numbers. And when we use the quantum numbers, it's actually truly a thing of beauty on the periodic table. And maybe another video, I will show you quantum numbers and how that relates to the organization of the periodic table. It's truly a thing of beauty. All right. So that's our first question is, how is the modern periodic table organized? The short answer is atomic number, number of protons. Henry Moseley was the one in 1913 to organize the periodic table as such. Dmitri Mendeleev is the father of the periodic table and organized the periodic table according to chemical and physical properties, but in 1869. And it was organized at his point in time according to atomic mass. We don't do that anymore. I've shown you 3 different isotopes of hydrogen, but you should see that this Z, the Z, is the atomic number. The A and the Z are German root words, by the way, just so that you are familiar with those, but this Z is meaning number in German. Why we use the letter Z, okay? All right, so let's get on to the next question and figure out what that one is. Here we go. So we've got that one handled, and the next question, we'll cross out number 1. And the next question here is, what is the trend in size, that is the atomic radius, going down a group on the periodic table, and why does this occur? All right, so we're going to pull out another periodic table, and we're looking for the trend in size, and why does this occur? So let's pull out another periodic table, and let's see if we can nail this question down here. All right. Fantastic. So what is a trend in size going down a group? That's the atomic radius and on the periodic table, and why does this occur? So the trend in atomic size or atomic radius is that one moves down a group or family. So you should be familiar that this is group 1, this is group 2, this is the alkaline metals, that's excluding hydrogen, or the alkaline earth metals, okay? So as one moves down a group or a family, this is group 1 or family 1, or group 2, family 2. These are vertical columns on the periodic table. So these groups or families are vertical columns on the periodic table. So any vertical column is a group or a family, okay? The size increases as you go down a group, okay? This size increase is because of the increase in the principal quantum number n. This is also known as the shell. So let me write that down here for you really quickly here. What is the n? And so everyone should be familiar with this from quantum numbers. So n of 1, 2, 3, 4, 5, 6, and 7. So these are n values. That is actually the principal quantum number, and this would be otherwise known as periods. So these are the periods on the periodic table, and these are horizontal sections on the periodic table. So for example, this is period 5, and this would be period 2. All along here, this horizontal section is period 2. And my red pin now is in between period 2 and period 3. There's no in between, but I'm just showing that period 2 is above the red pin, period 3 is below the red pin. And let's say we can do period 7 right here where the blue pin is. It's horizontal sections on the periodic table. The size increases because the increase in principal quantum number, that is n, that's our n, and that is also known as the shell. So n is equal to the principal quantum number. And this is the shell. So maybe you might hear your instructor talk about this or something like that. It's called the shell, which is a reflection of the increasing average distance of the atomic orbital from the nucleus as the principal quantum number n increases. As in n equals 1 is the closest to the nucleus, that would be hydrogen and helium. Hydrogen and helium. N equals 2 would be like lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, and n equals 2, they're further from the nucleus as the principal quantum number has increased. Okay, furthermore, as the principal principal quantum number, n, increases, the distance from the nucleus always increases, but less and less and further as one moves from the nucleus. So actually, there's a very large distance initially with n equals 1, and then n equals 2, n equals 3. So we're talking about the nucleus in the middle, and n equals 1. And then right outside of that would be another shell, and that would be n equals 2. And then outside of that would be n equals 3. And they do not get, they are not equal distance away from each other, but they do increase as you get further from the nucleus. So just so that you understand that concept, that you do get further from the nucleus as you go down a group or family. All right, so hopefully we nailed that one down with a little bit more information here on that as well. Boom. All right, now our next question right here on our periodic trends worksheet is, what is the trend in size, that is atomic radius, within the same group going to the right, and why does this occur within the same, sorry, not within the same group, but within the same period. So let me repeat that again. What is the trend in size, that is the atomic radius, within the same period? Within the same period, remember that's a horizontal section, going to the right, and why does this occur? So again, we're going to pull out that same periodic table that I had before so that you can see that here. And remember, I am the crazy hat chemist. All right, so here we go. The trend in size or atomic radius as one moves to the left, from the left to the right. So we're moving in this direction right here, from the left to the right. There is our left, there is our right. So for example, sodium to magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. We're moving to the right. Okay. Let's see here. So as we move to the right, there's a decrease in size. The reason for this is because the principal quantum number n remains constant. So we're in the same period, which is n of 3. So this value remains constant. Okay. So the period itself does not change. As you move in, for example, period 4, the n remains constant, okay? But the effective nuclear charge increases as protons are added to the nucleus. So the number of protons, as you can see, the atomic number is the number of protons, increases as you go to the right. But you still maintain the n value constant as you move to the right. Okay, so for example, this is actually a 3D orbital here, starting with scandium all the way through zinc. So you are maintaining that n value as you move to the right. So you're adding more and more protons as you move to the right. And then you are adding electrons to an orbital of which has already been established. Okay, so those electrons are added, but they are added to shells which have already been established. This is that the period does not change. So the effective nuclear charge increases, drawing the electrons towards the nucleus and decreasing the size as the atomic number increases within the group. So for example, scandium is going to be larger than zinc will be. And for the simple reason that scandium has fewer protons and the same n value than zinc does. Zinc has more protons and more electrons too, but those electrons are in orbitals that have already been established. So that effective nuclear charge, that is the increase in the number of protons, draws the electrons slightly closer together towards the nucleus. All right, okay, hopefully we got that one nailed. Let's go for our next one here. Number 4. Number 4 is list the 7 diatomic elements, writing their correct formulas. All right, so let's do that here. All right, so the 7 diatomic elements here, I'm going to use a new periodic table. I'm going to do a little bit of folding right here. so that you can see all of them that we're going to write down. Okay. Fantastic. All right, so the 7 diatomics are the following, and I will highlight them, okay? And so we have nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. So those are the 7 diatomics. And what is their formula? The formula for nitrogen is N2. The formula for oxygen is O2. The formula for fluorine is F2. The formula for chlorine is Cl2. The formula for bromine is Br2. The formula for iodine is I2. The formula for hydrogen is H2. Okay, so the word diatomic, the word di means 2, and then atom. So this is a 2-atom molecule. So these are the only 7 elements on the periodic table that have 2 atoms to make a molecular a molecule of that element. So nitrogen, the nitrogen that you breathe, 78% of it is N2. The oxygen that you breathe is O2. It's just not an O. Okay. So diatomic is derived from that prefix of 2, which means 2, and then atomic means atom, of course, and therefore this is a diatomic 2-atom molecule. Okay. Here is a hint on how to obtain the 7 diatomic elements from the periodic table. Take your right hand and make a gun. So there's my right hand. I'll zoom on out here. I'm going to make a gun with my right hand. See that? Bang, 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 bang. Okay. Or this is otherwise known as an L, but for most people, we'll just still stick with this right here. This L, you're going to stick it on your forehead, just like such. Just stick it on your forehead like that. Okay. And this is our greeting, how we greet people in the hallway or at the grocery store or something like this. And normally this means if you have an L on your forehead that you are a loser. But in this particular case, it does not. So what you're going to do is you're going to stick this right on your forehead, just like pop it on there. And then what you're going to do is you're going to take the point end of the gun, the barrel end of the gun, and then from your forehead, point it down. And then you see that there's a 7 that you get. So this is the 7 that you get. And so that way you always remember. And what you can do is you can place this 7 directly right here on the periodic table. Bam, and you see that 7. Okay, so these diatomics are identified with a shape on the periodic table. Okay, and this only gives you, sadly, the nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, and you can count that, and that is 6. And then what you're going to remember is that you need to jump to the next one, which is hydrogen. And if I unfold this periodic table, you can see that hydrogen is far away from the rest of the diatomics here. Okay, certainly, right? Is almost as far away as you can possibly get it, but it is not quite as far away as it possibly can go. So here's just another way to remember this. There's a game called chess, right? We got chess, we got checkers. So hopefully you're familiar with the game of chess. And there is a chess piece that is the most unusual in its movement of its pattern, and that is the knight or the horse. And so the knight or the horse is the knight is the only piece that actually can jump. So you're going to use these 7 here, and then you're going to, or sorry, these 6 right here, and then you're going to jump over to the hydrogen, and that is your 7th diatomic. That is one way to remember this. And so now you know how to greet people in the hallway, at the grocery store, at the gas station, when you're walking in the city. You're going to put that L on your forehead to recognize that you're going to tell them the story about diatomics and how you know what the diatomics are. Okay, fantastic. All right, so let's move on to the next question here. Now that we got our diatomics settled, okay, and let's go for this next one here. Number 5, it says, what is meant by the term electronegativity? Okay, and electronegativity, and then here is the symbol for electronegativity. It's kind of like a capital scripted X. Okay, And so what we can do is do this here. That's what we'll do. Here we go. What is meant by the term electronegativity? That's our question right here. And let's write down the answer for this. Okay, electronegativity. Okay, so electronegativity and this scripted kind of X there is the measurement. Hopefully you can read my writing, but at least you can hear me speaking here. Electronegativity, that scripted X, is the measurement of an atom's attraction to bonded electrons or an atom's tendency to attract electrons to itself. So that's the definition of electronegativity. Electronegativity, the scripted X, is the measurement of an atom's attraction to bonded electrons or an atom's tendency to attract electrons to itself. All right, really simple. Okay, we're going to figure out in a little bit more about electronegativity, and that is used certainly in the next unit when we talk about covalent bonding. So we absolutely need to know what electronegativity is and how to apply it and use it. So that's going to be critical in the next unit. All right, just so that you know. All right, the next one, number 6. And so we'll flip this little piece of paper here, and it says, number 6, what is meant by the term ionization energy, IE? So ionization energy, so ionization energy, IE, okay, is the energy cost to remove an electron. So ionization energy, IE, is the energy cost to remove an electron from the gaseous state of an atom or an ion. All right, that's our formal definition of ionization energy. Ionization energy, IE, is the energy cost to remove an electron from the gaseous state of an atom or an ion. All right, cool. All right, so let's go on to the next one here. All right, number 7 is what are the metalloids or semimetals, and list them that are on the periodic table. Okay, so we're going to grab ourselves another periodic table here so that we can get to the metalloids or the semimetals. Okay, so need some weights here. All right, so most commonly, most periodic tables that you find online or in your textbook will have this orange, and I have it in red, this staircase line, such like this, okay? And the metalloids are going to be on either side of this staircase line, but except for one, for the most part, okay? So the semimetals or metalloids. So semimetals or metalloids would be the following elements. B, SiGeAsSBTE, or one of these two, PO or AT. Now, typically most textbooks say, hey, how many semimetals or metalloids do you have? You typically have 7. So just like the diatomics, there are 7 diatomics or 7 metalloids. And I'm a little bit old school, and this is why I'm doing 7 right here. So it's effectively on either side of this staircase line. So if you're able to draw this red-orange staircase line, of which I have right here, and then go back and forth, but not aluminum, then you should be able to get the 7 metalloids. Those are what most textbooks use. Okay, so we got 7 diatomic, 7 metalloids, and those are our 7 metalloids. All right. Okay, fantastic. So let's peel this away and see what we can do for our next problem. I made a couple of nice weights and sketched some stuff in there to recognize that, hey, I am the crazy head chemist. Yeah, okay. Here we go. We got that one handled. Number 8, what separates the metals from the nonmetals on the periodic table? So I'm actually going to zip this over here again, and we have what separates the metals from the nonmetals on the periodic table. So I'm going to write this out here, and maybe I can get myself a Sharpie here. That will suffice, I believe. So you should see that on this left-hand side of this staircase line are the metals. And that would be on the left-hand side of this staircase line. On the right-hand side of this staircase line are the nonmetals. Okay, so that's generically what we discuss as the metals and the nonmetals. And most commonly, this is an orange staircase line, and this is the black and white version that's on the periodic table. Remember, not everything is black and white. There's a lot of gray in life. But in this particular case, the metals are on the left-hand side. Of course, hydrogen is not a metal, and it's on the left-hand side. And the nonmetals are on the right-hand side. And this is excluding the semimetals or the metalloids that I just discussed. But that is the generic classification right there. All right, fantastic. We got that one nailed down. Well, so let's see what we can do. What are the defining characteristics of metals, and what are the defining characteristics of non-metals? Okay, so let's see if we can sketch those out for what are the defining characteristics for metals and non-metals. All right. So what are the defining characteristics of metals? So we're just going to write them out. Number 1, for metals. Okay, so for metals are solids at room temperature. That's RT for room temperature. There is an exception to this, and that is mercury. That's the element Hg. Okay, so mercury is the single exception to this, and mercury is a liquid at room temperature. Okay, so hopefully you have that. Okay, metals have high luster. And you may ask, what is luster? Luster is, it's shiny. So for example, my wedding ring that's made out of platinum is very shiny. This is a piece of brass, and this is most certainly shiny, as well as this weight is shiny as well. Okay, so you can polish metals. Number 3, metals are good conductors of heat. So metals are good conductors of heat. So that means that, for example, this metal right here, if my room is rather chilly right now, so this metal, if I were to touch it, as I touch it right now, this metal is rather chilly. It's kind of cold. Okay. All right. That means it's a good conductor of heat. Furthermore, if I were to go outside and it'd be really hot and sunny outside, and if I were to touch the hood of a car, it would be very warm. All right. Number 4. Okay. So 1, 2, 3, and 4. Metals are good conductors of electricity. That means that they conduct electricity. Okay. Number 5. Metals are malleable. And that means that they can be rolled into sheets. So for example, aluminum foil. Aluminum is a metal and it's malleable and you can roll it into sheets. It's not called tin foil, by the way. It's aluminum foil. Number 6, metals are ductile. That means they don't quack like a duck. No, that means that they can be drawn into wires. And I'm hoping you're familiar with any kind of metal, copper wire, for example. That's a perfect example of something that's copper. That's a metal. Metals have high density. Hence, going back to number 1, they're mostly solids at room temperature, except for mercury, which of course has high density anyways. And number 8, we're just going to do 8 of these, have metals have high melting points. So these are the characteristics of metals, and I'll repeat that. Metals are solids at room temperature, RT, except for mercury, which is a liquid, of course. Number 2, metals have high luster, that is, they are shiny. Number 3, metals are good conductors of heat. Number 4, metals are good conductors of electricity. Number 5, metals are malleable, that is, they can be rolled into sheets. Number 6, metals are ductile, they can be drawn into wires. Number 7, metals have high density, that is, high density is mass per unit volume. That is, they have a lot of mass for a relatively small volume. And metals, finally, have a high melting point. That is, again, they are solids at room temperature and pressure. Okay. All right. So those are the characteristics of metals. And really, the really nice thing about the characteristics of metals and the characteristics of nonmetals. So I'm going to do the nonmetals in black. They are not necessarily solids at room temperature and pressure. In fact, nonmetals are solids, liquids, and gases. Okay. Nonmetals have low luster. Nonmetals are poor conductors of heat. Nonmetals are poor conductors of electricity. Nonmetals are not malleable. Nonmetals are not ductile. Nonmetals have low density. Nonmetals have low melting points. So you can see that metals and nonmetals have opposite characteristics. They are a shared set of opposite characteristics for metals and nonmetals. So make sure that you understand the metals are in the blue and the nonmetals are in the black with the slight changes to the blue. All right. All right, fantastic. Hopefully you've got that pretty much nailed right there. Boom. I am the Crazy Hat Chemist, and all these videos are brought to you by the Crazy Hat Chemist. So keep on watching. There's more Crazy Hat stuff coming your way. And yeah, this is fun stuff. This is cool chemistry stuff. I love it. You got to love it too. All right. All right, so let's see if we can get on to this next question right here. So let's flip this around here and number 10. Number 10. Let's slide number 10 on up so we can see number 10 here. All right, number 10 is a kind of a big complicated question. And it is number 10 is what is the shielding effect that is screening and how does it play a role across a period? Okay, so we know that periods are horizontal sections on the periodic table, not vertical sections. So let's write out what is the shielding effect. The shielding effect is the decrease in the attraction between an electron and these electrons most commonly are the outermost electrons. So commonly and the nuclear charge. And that is the nuclear charge is that positive charge of the proton. So positive charge due to protons, right? Because the neutrons are neutral, right? And this is, so the shielding effect is the decrease in the attraction between an electron, commonly the outer electron, and the nuclear charge, the positive charge due to the protons. And this is due to the other electrons in the atom. Let's do to other electrons in the atom. Most commonly the inner electrons. Okay, so that's the shielding effect. And then the consequence of this, like how does this play a role? So the consequence of the shielding effect. Let's see if we can get all this. I'm not sure if we'll be able to make this all on here. Is that as one moves from left to right, within a period, the shielding effect remains constant. Yet the nuclear charge increases. And we just talked about nuclear charge earlier. Um, and so as the nuclear charge increases, the size going from left to right decreases. Perfect. So what is the shielding effect? The shielding effect is the decrease in the attraction between an electron, commonly the outer electrons, and the nuclear charge, the positive charge due to the protons. And this is due to other electrons in the atom, most commonly the inner electrons. The consequence of the shielding effect is that as one moves from left to right within a period, the shielding effect remains constant, yet the nuclear charge increases. The size going from left to right decreases. So let me kind of draw this out for you here. So this is still the shielding effect, and let me see if I can, I'm not sure if I can get all this in here, but let's see if we can draw this out here. So we have the positive charge of the protons on the inside in the nucleus. And then we have these electrons right over here in these shells. And so then there would be an electron on the outside over here. Well, this is kind of like this electron, this outermost electron, would like to interact with that positive charge of the proton. But unfortunately, what has been happening is that it is being shielded by these inner electrons. These inner electrons are preventing this black electron that's on the outside from getting near the positive red proton charge in the nucleus. Consequently, the positive charge increases, and you add electrons to these shells that are already here, and that positive charge increases, drawing these electrons in a little bit more. That is as you go across a period. But if you just were to look at this with one electron, then that one electron is being pushed a little bit further away. And that causes this to get slightly moving outside, a little bit larger. All right. All right. So shielding effect, complicated terminology there. All right. So let's figure out what our next question is. And let's see if we can pop this in here. Here we go. So we got this down. What's the definition of metals and nonmetals? We got the shielding effect in. What are the predicted charges of elements on the periodic table? Label as many as you can. Oh my, oh my. So let's see what we can do here. We're going to pull out a periodic table, and we are going to write down as many as the predicted charges as are possible. Okay. Bam. Let's see if we can do this. I'm going to put this right over here. And here we go. Predicted charges. Everything in group 1 is a 1 plus charge. Then what we have is a 2 plus charge, a 3 plus charge, a 4 plus charge, and then a 5 plus charge. And what's the Roman numeral for 5? That's a V. So hopefully that makes sense. We're going to go 1, 2, 3, 4, 5. These are all cations. That is, they lose electrons. Cations are positive, kind of like cats. They have paws. They're positive. All right, I didn't just do that meow on here. Okay, but yeah, you got that. Okay, cats and cations, they're positive. So now that you counted to 5, now what you're going to do is count 5 more elements. Okay, so here we go. 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5. These 5 elements, okay, chromium, manganese, iron, cobalt, and nickel have a 2 plus and a 3 plus charge. If it is a 2 plus charge, the common name has an OUS ending. If it has a 3 plus charge, then the higher charge has an ic ending. Remember, it doesn't mean that 2 plus goes to OUS, doesn't mean that 3 plus goes to ic. It's the lower charge is the OUS, the higher charge is the ic, and I'll show you that here in just a moment. So you've been traveling along the freeway going at a pace of 1, 2, 3, 4, and 5. You're increasing your pace, and then you're going along the freeway at 2s and 3s. And now what you're going to do is you're going to see someone behind your rear view mirror, and you're going to see some lights. And who is that? That is a copper. And copper is going to force you to slow down to a charge of 1 and 2. plus. So the OUS ending on cuprous, that would have a 1 plus, and the ic ending on that, the cupric, would have the 2 plus charge. So this would be ferrous and ferric, cobaltus and cobaltic, nicholas and nicholic. But this is cuprous and cupric. All right. Now we have a diagonal pattern of 1, 2, and 3, and then in the same column as zinc is cadmium. So these 4 elements have a single charge of a 1 plus for silver, a 2 plus for the zinc, and a 3 plus for the aluminum. And since zinc and cadmium are in the same column, then that's a 2 plus for those two. All right. Then we also have gold and mercury. And gold is in the same column as copper and silver. And since copper and silver have the same common charge of a 1 plus, then that means that there is a 1 plus charge for gold, and that's Orus. And then gold is worth more than copper or silver, so therefore it has the higher charge of the 3, and that would be a 3 plus charge. So that's auric. So Orus, auric. All right, then we have mercury, and there's a 1 plus charge on mercury, and that's mercurus. And then there's a 2 plus charge on mercury, and that's mercuric. And so it's kind of like mercury is right down here, and it's intersecting this column and this column with a 1, the common charge, and a 2. We also have 2 other elements right over here that go up and down of each other. That's tin and lead. And tin and lead have the same 2 charges, and that's a 2 plus and a 4 plus. The 2 plus and a 4 plus for both the tin and the lead. All right. All right, so fantastic. So we're going to come back over here and go 1 and 2 plus, and then we're going to skip this transition element region, and we're going to go 3 plus. And then we're going to go 4 plus and maybe a 4 minus. So there is my change right there. Now, if you remember before, we had talked about the dividing line between the metals and the non-metals, and that's most commonly this orange staircase line. To the left are the metals, to the right are the non-metals. So metals lose electrons and they form cations, and nonmetals gain electrons and they form anions. So the noble gases are in this column, and they don't have a charge because they do not lose or gain electrons. But the halogens, fluorine, chlorine, bromine, and iodine, becoming halide ions, would have a -1 charge. Then oxygen and everything in its column would be -2, and then -3 for the nitrogen column, and sometimes here -4 for that carbon column. All right, and I think that that is the vast majority of the charges on the periodic table, and these are also periodic trends. So you should be familiar with the periodic trends on the periodic table and their location, and you should be able to like hammer these out really quickly, and these go with their specific groupings and their namings. All right, hopefully you got that. That's looking pretty good. All right, this is going to be part 1 in our series, and we are going to continue. We have 45 questions on this worksheet, so we have only done up to number 11 at this moment in time. I am the Crazy Hat Chemist, and you can find me on YouTube and watch some of my awesome, hopefully awesome videos if you enjoy that. You can even watch some of my cooking videos on YouTube. So that would be crazy if you were to watch some of my cooking videos. Anyways, I hope you have a great day, and I'm going to see you next time for another awesome, cool, crazy video. So talk to you then. Bye for now.